In this screencast, we'll begin to talk about linear programming. This is part 1, optimization problems and constraints. And this will be a multi-cast series, as there have been a few of those on this channel. So this is the first part. So linear programming is an optimization technique. So there are lots of optimization problems in various branches, such as social science, management. Primarily, optimization problems occur in logistics. So when you need to optimize a route or optimize some resource allocation, maybe do some scheduling. So you have a problem which is characterized by a set of constraints. Another area of another domain of application is management. So typically you have a problem, an optimization problem. Let's talk about what exactly is an optimization problem. So an optimization problem is a problem that has a set of independent variables. So each of those independent variables corresponds to a quantity. Now further, we can put other constraints on the values of those independent variables. Let's say that they have to be all non-negative, for example, right? And then we will have a dependent quantity, dependent in the sense that, maybe multiple dependent quantities, but typically one dependent quantity, dependent in the sense that it depends on the values of the independent variables. So this is the first part of the definition of an optimization problem. And the second part of the definition of optimization problem is that you have a set of constraints on variables and quantities. So what exactly those quantities are? A typical constraint is, say, the range. Right? We can constrain the value. Right? There are multiple ways to constrain a variable. So in linear programming, and that's actually where it derives its name, linear programming, all constraints are linear equations. So if we look at a set of constraints and we can check that they're all linear equations, then chances are we're dealing with a linear optimization problem and we may be able to, not all the time, but sometimes we can solve it via linear programming methods. So these are examples of constraints for x plus 5y minus 10z, and this another constraint is 10 times x1 plus 15 times x3 plus 255 times x4. So those variables are domain, the definition of those variables are domain dependent. So let's just make the theory component of this screencast a little bit more concrete and set up a simple example. It's one of the original problems, types of problems that were solved in linear programming, by linear programming. So let's say that we have a simple diet management problem, and let's say that I eat apples and milk, right? That's my diet, right? And so there's an apple, then there's milk, and let's just further simplify it to talk about, to discuss, to constrain the problem to two nutrients. Calcium, that's the first nutrient, and then the second nutrient will be iron. So my diet consists of apples and milk, and the two nutrients that I am concerned with is calcium and diet. Let's say that after careful measurements, I know that each apple contains 0.15 grams of calcium and let's say 1.5 milligrams of iron, and a glass of milk contains, let's say, 0.3. I'm just making these numbers up, but I hope that they're roughly correct, 0.3 grams of calcium and 0.4 milligrams of iron, right? So then I talk with my dietitian, and my dietitian says that let's say I have to my diet, right, that consists of apples and milk, must have the amount of calcium is less than at least 0.9 grams, right? Greater than or equal to 0.9 grams. And then the amount of iron in my diet. The amount of iron in my diet, I wrote milk, it should be iron. The amount of iron in my diet should be 11 milligrams, right? So, well, then there's an issue of cost. So the amount of I wrote the amount of milk, but it should be the amount of iron, right? And then there's the issue of costs. So let's assume that one apple costs me 0.9 units, some monetary units of exchange. Let's say bitcoins. And one glass of milk costs me 1.2 units of exchange. So let's agree to that A will stand for the number of apples that I eat, and milk stands for the number of glasses of milk that I drink. So then the cost function takes the number of apples and the number of glasses of milk, and so it is defined as a linear function, right? So 0.9 times A, the cost of apples plus 1.2 times M, right? The cost of milk, and it's a linear function. Okay. All right, let me go here. Okay. So then the calcium amount in my diet is the amount of calcium in apples plus the amount of calcium in milk. So by the table, it's 0.5 times the number of apples plus 0.3 times M. That's the number of glasses of milk, right? So that's the first column of the table. And then as for the iron, right, the amount of iron, it will be the second column, right? Every apple that I consume contains 1.5 milligrams of milk, so and then every glass of iron, and every glass of milk is contains 0.4 milligrams of iron, right? It's just it's very important for us to keep this. Milk is a consumable product, and iron is a nutrient. So we're interested in nutrients now. So 1.5 times, or let me erase this just to make it clear. That's 1.5 times A. That's the amount of iron in apples plus 0.4 times M. That's the milligrams. That's the amount of iron in glasses of milk. So what we need to do, right, in this problem is we need to minimize the function cost, the cost function, right, written just above, in such a way that the dietary requirements are observed. In other words, 0.15 times A plus 0.3 times A has to be greater than, that's the amount of calcium, has to be greater than 0.9 grams, and the amount of iron has to be greater than or equal to 11 mg. 1.5 A plus 0.4 M has to be greater than 11 milligrams. All right, that's the second dietary requirement. It says the amount of milk greater than or equal to 11 mg, but it's actually the amount of iron, as I pointed out before. So these are the three. Let me grab a different color. These are the three linear constraints So the first, the second, and then the third one is 1.5a plus 0.4m. This is the second constraint. This is the third constraint that our problem is subject to. And this is a linear programming problem. Okay, we'll continue in the next screencast. Thanks for watching.